All right, today what we're going to look at are two things, ratio and proportions. So we're going to write ratios. Notice that ratios aren't solving, ratios are writing. And we are going to solve proportions, which do use ratios. So by way of introduction, let's see here. The table at the right shows the wins and losses of a particular baseball team going along special years. In which years did the team have the best records explained? If we consider this one as trying to go the simplest possible route, if you take the number of wins you have, the 60, and divide it by 24, we start off with this ratio. But notice that each one of these, if I do it again, the 110 divided by 44, even if I reduce the fractions, because we have different denominators, it's hard for us to tell which number is going to be the largest, because ultimately in this scenario, I want more wins than I want losses. So every one loss, I have 3 wins. Every one loss, I have 16 wins, something like that. So the easiest thing to do is actually just plug that into a calculator to see what you get. So here we get 2.5, but I'm going to keep it as a ratio. Why? Because originally we're talking about 2.5 wins per 1 loss. So this is the only time in math when we do not get rid of and ignore the 1 in the denominator. Because a ratio is comparing two numbers that have the same units, but it's also giving us the idea of of how many of these we have. So 2.5 wins to 1 loss. So when we simplify this one here, also 2.5 to 1. What do we automatically know about the next one there? So since these have the same wins, but this one has more losses, clearly we know this ratio is going to be lower. So because the question just says the best record, I can effectively ignore 1970. And the last one here is 108 over 54, and plug that in. Exactly 2. So in which year, and notice here it says years, potentially. So our final answer is this. In 1890 and in 1930, they had the best years with a ratio of 2.5 wins to 1 loss. And there we go. What we're going to do today is look at ratio and proportion primarily. But in order to understand them, we're going to have some vocabulary here. First off, ratio. So a ratio is a comparison of two numbers. But the numbers have to have the same type of units. So notice what I say, the same type of units. So for example, if I said 7 inches to 3 feet, technically that is a ratio. Why? Because what do inches and feet both measure? It measures distance. So in the same way, if I said 3 wins for every 1 loss. Well, what are these? What are wins and losses? They're games, right? So, they're results of a game, essentially. So, in this case, we're saying that we can always convert the units if we want it to be, so that we can ignore the units. That's ultimately what we're saying with a ratio. A rate, on the other hand, is a comparison of two numbers with different units. So, for example, you're driving on the highway at 70 miles per hour. That's per 1 hour. Or you get 16 miles to the gallon. And notice these are called unit rates, because there's a 1 in the denominator that we're not mentioning. But it doesn't have to be a 1. I could say something like this. I get 37 cats per $100. 34 cats for $100. So that would be a rate, about how many cats you can get in $100. A proportion is something we solve generally, and it is a ratio equals a ratio, essentially. In other words, two fractions equal to each other. So generally speaking, when we have a ratio, it looks like this. And I'm going to use these letters, A over B equals B over C. And notice that I color coordinated these. Yay for color coordination. Why? Because of this reason. The A and the D, in the position that they are, kind of like this is the first one you come to and this is the last one, those two are called extremes. They actually have names. And the B and the C, and then we're not saying together B times C, I'm just saying the B and the C. Those are called means. In other words, A and D are the farthest out you are from the fraction. You start here and you end here when you read the fraction. A over B equals C over D. And the means are the way to get there, if you think of it like that. The only way to get to D is if I go through B and C by reading it. So those are called the extremes and means. And last vocabulario that we want to talk about is called the extended proportion. Extended proportion. I forgot to mention, so let me go back to here real quick. A ratio can be written in a couple different ways. Number one, you can write it as a fraction, 7 over 3. Another way you can write it is this, 7 colon 3. And another way you can write it is like this, 7, the word 2, and say 3. But they all read the same way. 7 to 3, 7 to 3, 7 to 3. In math, the most common is this as our answers. You might often see this as a setup, but generally speaking, we're going to interpret each one of these to be a fraction so that we can manipulate it mathematically. And sometimes you'll see this, especially when it's talking about like in college. Oh, there's a 20-to-1 ratio of students to teachers. And you're like, oh, 20-to-1, that's pretty good. As opposed to going to a large university where there might be 300-to-1, so you don't get as much personal attention maybe. The last thing we're going to look at is an extended proportion. And an extended proportion is this. It's just a fraction that goes on. Or, so it can read like this, 3 to 4 to 5. And you say, well, how do you write that as a fraction? Well, sometimes we don't actually need to, but if you did want to, because you were having a hard day, you would write it like this, 3 over 4 over 5. We do not tend to do that. We do not tend to do that. We tend to interpret this in a different way, but that's what's called an extended proportion. So it just goes on, and what we get out of this are different fractions, 3 over 5, 3 over 4. We'll explain that tomorrow when we come back here. Conversions, welcome to the English system, which kind of makes sense if you think about it, because how many inches are in a foot? 12. Now, why is 12 a nice number?
Divides in half.
It divides in half, divides in thirds, and divides in fourths. And in fact, divides by 6 too. So it has a lot of factors. 10 only divides by 5 and 2. So it's hard to cut 10 into fourths without going into decimals and fractions. But 12 you can divide into fourths and into thirds as well. So pre-calculators, that's 12 is probably a good number there. Ounces, how many pounds in an ounce? 16. I mean the other way around, ounces in a pound. 16 ounces is correct. No clue why. 3 yards in a foot. 3 feet in a yard. Question? 10, of course, 10 millimeters. And miles. Anyone? Any inches? Feet in a mile? Call it out. 5280. All right, I think some of you got one of those digits right. Good job. 100 centimeters, hence the name centi. Centi means 100. Why it's 5,280? No clue. Offhand, I don't know. All right, writing a ratio. A ratio of a salad plate, 8 inches, to the dinner plate. So the salad plate comes first, and the dinner plate comes second. So if you wrote it as a fraction, it looks like this, to 1 foot. But generally speaking, what we're going to do is convert it all to the same units. How do we convert to the same units? All right, so if we multiply this by 12, because there are 12 inches in 1 foot, now we have 8 over 12. And notice, I'm going to write the inches for now, but what happens when you divide inches by inches? They drop out. So we don't even need the units anymore. Units are just like everything else in math. They can be multiplied, they can be squared, they can be divided, etc. Now we just reduce. I'm going to divide by 4 there to get 2/3. So the answer is 2 to 3, or 2/3. It's also sometimes written like this. You don't have to write all this. Or you could say 2 with the number 2, or the word 2, 3. But let's keep, unless it says specifically to write it in a different way, generally let's write it as a fraction. Now let's use ratios to solve. We're not going to solve proportions. We're going to use the ratios to create equations that aren't necessarily proportions. So here, the perimeter of a rectangle is 280 centimeters. The ratio of the width to the length is 3 to 4. So what's the length of the rectangle? Well, the key thing here is actually the perimeter. What's
Other 1 times 2.
So 2L plus 2W is going to give you your perimeter. So we're going to use exactly this formula. The issue is we have 2 variables, and we want to unhave 2 variables. So what can we do? Well, it turns out that since our ratio is 3 to 4, let's think about what that means. We actually don't know the actual length, but we know that when you divide them and put it in simplest form, you get 3 over 4, which means it could be double. It could be 6 and 8. It could be triple, where I have 9 and 12. It could be times 10, where this is 30 and this is 40. We don't know. In other words, we multiply by something we don't know. In fact, we could be dividing as well. It could be a fraction I'm multiplying by. So instead of putting in L and W, I'm going to put in 3x and 4x. So let's see. It says the width compared to the length. So it says that the width is going to be smaller than the length. So effectively, I know the width is 3x, and I know the length is 4x. So I'm going to substitute the 3x and the 4x in. So I'm going to bring down the 2, but instead of L, I'm going to put 4x in. Then I'm going to bring down the, instead of bringing down the W, I'm going to bring down the 3x. Like so. And the perimeter, they actually told me, is some great number, 280. Y'all. I'll temporarily ignore the centimeters and bring that back in a minute. So now we just use our algebra skills to double things here. This is 8x. This is 6x. If you need to see the next step, I'll write it, but you could just do that part in your head. So we get 8x plus 6x. All right, and then to finish this up, I get 14x equals 280. Notice this is not going to give me the answer. This is just going to give me the value of x. So I have to plug it back in. So x is going to be 20. So I have to substitute that back in, and remember we're looking for L, the length, so I have to say 4x. So when I multiply by 4, L equals 4 times 20, so the answer is 80 centimeters is my length. I know I'm right because 3/4 of that is 60, and when I say twice 60 plus twice this, I should get 280. The lengths of the sides of a triangle are in extended ratio here of 3 to 6 to 8. So the triangle's perimeter is 5, 10. So notice that the perimeter of a triangle is just the sum of the sides, as if we're saying A plus B plus C. So again, all we do is substitute here the 3x plus the 6x plus the 8x, and that's going to add to 510. Continuing on, 17x equals 510. So x is going to give me, so now we have 30, and it asks what are the lengths of the sides. So we need to know all the sides. So I'm going to plug it back in. So one of the side length is 90 centimeters. Another one is 180 centimeters. And the last one is 240 centimeters. The only way to check this is just to do a quick division here, but in a sense we already did that because there's no equation necessarily that says we're not adding these to 180 because they're not degrees, etc. The last thing we're going to look at here is just solving proportions, and I will do A and B, and then you will work on the next two in class. All right, so let's see here. Most likely you are familiar with the concept of cross multiplying. So let me just real quick refresh what we mean by that is when we cross multiply, these two become one number or one side, and then the other side is the product of these two here, 4 times 13, which is coincidentally 52. And now when we solve for x, divide by 52, you end up getting x is 1. Of course, we know we're right because when I plug in a 1 here, I get 1/4, and when I simplify this side, I get 1/4. So we know that it works. But that's not the only way to have done it. Look at C. Do you have to cross multiply on this one? No. Not really. In fact, I didn't have to cross multiply on this one either. What could I have done? What's an alternate method to doing this one? So one way to do it is just reduce this by 13 to get 1/4. That would have coincidentally given me the answer because now the x in the numerator has to be 1. Did anyone see an alternate way of doing that? This. If I want to get this by itself, I need to get rid of the divide by 4. So how do I undo divide by 4? Good. Notice when I multiply both sides by 4, x is by itself. Cross multiply will pretty much always work, but you don't always have to do it. Notice over here, now when I reduce things, here I reduce to get 13 and 1, and so clearly we see that x is going to be 1. So there are alternate ways to do this. You can cross multiply, pretty much that will always work, but sometimes it's a little bit more work than need be. In this case, I will cross multiply, but don't forget that as I cross multiply, this 7 has to distribute to both terms. So I'm going to do that in the very first step. 7b plus 7. I had to distribute it to both terms in that other numerator, excuse me. And then I multiply those two together to get 1, 1, 2. Now we just solve like we normally do. 7b equals 105, and then b equals 15. We know we're right because if I put 15 back here, I get 16, and then I can divide both of those by 8. This gives me a 2, and this gives me a 7.